Okay, so if we were to take just a generic log base b of b to some power x. If you have some exponent inside your log that has the same base as the log itself, there's an inverse property that allows you kind of a shortcut. Because exponents and the logs are inverses of each other, when you do a combination of functions, when one is inside the other, you're just going to be equal, or going to be left with the value up here, this x value. And now, this is a general rule. So if you can follow this rule, if it's just given to you and you just follow it, that makes it easy. So if they had something to the effect of log base 3 of 3 squared, what's that going to equal based on that rule? The base of our log and the base of our power or exponent are the same, therefore your answer is just going to be 2. And so if you can follow this process, you can see quickly how you get to it. Now, if you want to verify it, or if you don't remember how this process works, the verification for this is if we were to take this original equation without the x, without setting it equal to x. So let's say I take this form, log base b of b to the x. And I don't know what it's equal to. I want to solve for it, or I want to verify that it is in fact equal to x. If I were to take this and I'm going to set it equal to y. And the process of this, the steps I'm taking are to demonstrate that the value for y is actually x. Because we're solving for this, or we're verifying that this purple relationship is correct. Okay, so if I just assign this equal to some unknown, I'm calling it y, and then rewrite the exponential form, I get b to the y is equal to what's inside the log, b to the x. So what does y actually equal? X. And so it verifies that what we had in purple is correct. Okay, so you can do it this way as well. You can do it the long way, or you can do it kind of this shortcut way. Okay, there's another way to kind of think of this shortcut way. And that is, again, let me verify. If I take log base b of b to the x, one of the properties that you will see in more detail in the next few sections is anytime you're dealing with a log, if there's a power inside of a log, that power can move out in front and it becomes a multiplier of our log. So again, a second way to kind of verify this is we can take this power of x and we can rewrite it in front. It becomes x times the log base b of b. Okay, and then anytime you have log base b of b, anytime the base inside and the base of your log is the exact same thing, these have a value of 1. Okay, so again, log base b of b is equal to 1. Now that should make sense, right? Exponential form. B to what power is equal to b? 1, right? So this whole thing becomes 1, which just leaves your answer x. Whatever this was, it dropped down in front. Log base b of b has a value of 1. That is your answer. And now I go through these two different ways of showing you things because you're going to get problems that look more like this. And so this one doesn't fit nicely into this pattern as it sits there, right? Log base 5 of 25 to the power of x. And you're asked to evaluate this using the inverse properties. Right? But in order to apply this property, you would need to make sure that the expression inside your log has the same base as the log itself. Can you rewrite 25 using base 5? Yeah, so if you were solving this problem, what you would do is you would set it equal to log base 5 of, and instead of 25, what could we write? 5 squared to the x. Okay, when you take a power to a power, what do you do with those powers? Multiply, so base 5 to the 2x, And now, again, you can apply the property right here, or you can move this out front. This becomes 2x times log base 5 of 5. And what is log base 5 of 5? Has a value of 1. It fits this pattern. And so that is just a multiplier of 1. Its identity property doesn't change the value at all. So you get your answer to be 2x for that. Okay. So try the following example. Log base 7 of 7 to the negative 3x. Okay, what is that going to simplify to? This is going to simplify to what? Yeah, just negative 3x, right? It fits the pattern right away. You can just do that. Or if you want, you can move this negative 3x out front. Log base 7 of 7, which has a value of 1. Multiplying by 1 won't change a value, so you get your answer, negative 3x. All right, so let's take one last one. It's, again, a little more difficult. It's not just the single step like that problem. Okay, so see if you can answer this question. Log base 2 of 64 to the power of x, what is that going to equal? Careful. Now you're just randomly guessing numbers. All right, so the idea is you take log base 2 of, and we want this base to be the same as the base of our log, 2 to the power of. So let's think about 64. A couple things you know are equivalent to 64, right? You should know 8 times 8 is 64. Okay. What is 8 in terms of a base 2? 2 to the what power equals 8? 6. Well, each 8. 2 to the third, right, is equal to 8. So if you take 2 cubed times 2 cubed, when you multiply exponents, you do what with their powers? Add them. So 3 plus 3 is 6. So really, 64 can be thought of as 2 to the 6th, that whole thing to the power of x. When you take a power to a power, you multiply 6x. And once we get to this form, we can bring this 6x out front. And log base 2 of 2 has a value of 1. So multiplying by 1 isn't going to change a value. We can eliminate that. And we're left with our answer, 6x. All right, questions on that? All right, so let's take a look at the other inverse property. Okay, this one beginning with our exponential form. So if we have an exponent with a base b, and in our power we have log with the same base, to some power, or log base b of x. Okay, so the base of our exponent and the base of our log are exactly the same. The inverse properties identify this as giving you a value of x. Okay, so whatever's inside this log winds up being your solution. So again, if you see this in just a real straightforward sense, if you have 8 to the power of log base 8 of 2x, what is that going to equal? The base of your exponent, the base of your log are the same, so it's just going to equal what's inside your log, which is 2x. Okay, so you can come up with your solution very quickly if it fits this pattern. And now, if you wanted to verify it or to see why that is true, if we were to just take the exponent b to the power of log base b of x. And we wanted to, again, just set this equal to some unknown. And we want to verify that y is in fact going to equal what we were told it was. Let's verify that y does equal x. Well, if we rewrite this in its logarithmic form, we take the log base b of whatever's on the other side, y, is equal to whatever's in the power, log base b of x. And so what does y have to equal? X. So again, the simplest thing is just to take whatever's inside the log, set that equal, and that's going to be your solution. Okay, so what if I take e to the ln of 20? The base of your exponent, the natural base e, is that the same as the base of your log in the power? Yeah. ln is a natural log. So what's this going to equal? 20. Okay, it just equals whatever's inside the log of your power. Okay, if we take another example, and again I'll use common log this time, I have a power or a base of 10 to the power of log of 3. Okay, what's that going to equal? The base of our exponent is 10. Our common log, again, if there's no subscripted number, it's an unwritten what? Base 10. So the 10 of the 10s are the same, so this is just going to equal 3. And so that's the inverse property that you would see for that.